In this way, we can record you, because otherwise your voice will be lost. And we are trying to solve the microphone issues.
Okay, so this dynamics is related to the electric field, that is a combination of co-rotation and convection due to solar wind events. And then I will talk about the motion of the particle, and especially because they come from the ionosphere and refilling after the plasmasphere has been eroded. I will detail also the links that we have found with other regions of the magnetosphere, and especially with the radiation belts that overlap, in fact, the plasmasphere, but is filled by much more energetic particles. And then I will talk about the effects of waves and show some observations from different satellites, and especially image that give very nice views of the plasmasphere. Thus, the plasmasphere is located in the inner magnetosphere, thus where the magnetic field lines are closed. Thus, the magnetosphere of the Earth is just the region where the magnetic field of the Earth is dominant. And there are different particles that are trapped in this magnetic field, and especially these cold particles in the plasmasphere coming from the ionosphere. These particles have energy typically between 1 and 10 electron volts. This low energy, and but it is a quite dense region of the magnetosphere in comparison to the other regions of the magnetosphere, but of course a low density in comparison to the ionosphere, because the density decreases exponentially with the radial distance. And thus typically there are between 10 and 10,000 electrons per cubic centimeter in the plasmasphere. And it's mainly composed by protons, 90%, 10% of helium ions, plus traces of other ions from oxygen, nitrogen, and alpha particles. And you can see this, that there are also the radiation belts that overlap the plasmasphere. These radiation belts are populated with electrons, ultra-relativistic electrons with energy larger than 500 keV, and protons of several million electron volts. This is much more energetic, but present in less high quantities. But because of their energy, they are much more dangerous for spacecraft, and that's why they are often more studied than the plasmasphere itself. And then you can see also here the plasma sheet. This in the night side, you have this region populated with particles of several keV that will be accelerated along the magnetic field lines and be injected in the ionosphere at higher latitude and create aurora especially. So what is very important is the magnetic field of the Earth. This it is created in the liquid core of the Earth, and due to the rotation of the Earth on itself, this by a dynamo effect, it creates a magnetic field that is quasi-dipolar, but that forms an angle of 11 degrees with the axis of rotation. Thus the magnetic poles of the Earth do not correspond exactly to the geographic poles corresponding to the axis of rotation. For instance, in the North Hemisphere, it is located in Arctic Canada, the magnetic pole, thus quite far, well, more than 1,000 kilometers from the geographic pole. This dipole decrease as the cubic the magnetic field intensity in a dipole decrease as the cube of the radial distance, and is 2 times larger, for instance, at the surface of the Earth in the polar region than at the equator. But in fact, the magnetic field is not really a dipole because you have this compression in the direction of the sun, this day side, and on the contrary, the magnetic field lines are elongated in the night side. Typically, the magnetopause, the limit of the magnetosphere, is located at 10.
Okay.
Sorry, at 10 Earth radii in the direction of the sun. There's a more complete magnetic field that can be used is the International Geomagnetic Reference Field that take into account this compression, elongation, and local irregularities. And with 80 terms, you can reproduce the magnetic field of the Earth. So the plasmasphere is just this region of the inner magnetosphere. And what is very dynamic in the plasmasphere, it's the limit of the plasmasphere that is called the plasmapause. This plasmapause is located typically between 3 and 7 Earth radii in the equatorial plane. And well, it's you can observe a very sharp gradient at this region. This is, in fact, the region where the plasma is not anymore in co-rotation with the Earth, because the plasmasphere is in co-rotation with the Earth, contrary to the rest of the magnetosphere. And thus, this plasmapause corresponds to the region where the centrifugal force becomes larger than the gravity. This sharp plasmapause is due to the interchange instability mechanism. And thus, in fact, each time the activity increases, the zero parallel force surface comes closer to the Earth. Thus, the plasmasphere is then eroded, and you have this plasmapause that is closer to the Earth, and the plasmasphere that is more reduced. And you have also formation of a plume, as you can see in this simulation here. This here you can see this in our model. This the plasmasphere, this here in the equatorial magnetic plane, and here in the meridian plane. This in the equatorial plane, the plasmasphere is almost circular, but the distance depends on the geomagnetic activity level, given here by the Kp index. That is a 3-hour index going from 0 to 9, 0 when the activity is low, 9 when the activity is very high. And thus the activity, the geomagnetic activity increases when there are some events from the sun. Thus it can be a coronal mass ejection, but it can be also smaller events like a coronal hole, this higher bulk velocity, solar wind arriving at the Earth. And then this will disturb the space environment of the Earth, especially the magnetopause will come closer also to the Earth, and the plasmapause as well. Thus, this is due, in fact, to the currents that are created when the solar wind is deviated. The magnetic field protects us from the solar wind, thus it is deviated and creates at the magnetopause a current that flows here in the tail and in the neutral sheet. There are also, when there are events, you have injection of more particles here in the equatorial plane, in the ring current. And the ring current almost always exists, but it is intensified when there is a geomagnetic storm. And then it creates a lower, well, the magnetic field intensity and especially the horizontal component that is measured at the surface of the Earth is then lower. And thus that allows us to give the geomagnetic indices, and especially for the ring current, the DST, disturbed storm time indices. And then you have this also currents field line currents here, connecting the plasma sheet to the ionosphere at high latitude, also called Birkeland currents, and that will inject electrons in the auroral oval and create this also aurora, brighter aurora, when there are events. So typically, when you have a storm, you have to look at the parameters of the solar wind. This here, for instance, you see the number density of the solar wind. You can see a sharp increase here, associated also to a sharp increase of the bulk velocity of the solar wind. This generates a storm. You can see here that the index Kp, this Bartels index, this increase up to 7- here in a few hours, and then during the main phase of the storm, and after this, it is the recovery phase taking several days. And the DST, disturb sometime index, this that is more for the perturbation at the equatorial plane, while the Kp index shows the perturbation for all the planets. Then you can see a sharp decrease during the main phase. Here it's a quite intense storm because it's less than -100 nanotesla, and then again the recovery phase. And you can see also that often such storms are related to southward interplanetary magnetic field. Is the solar wind magnetic field, the Z component is negative, and this show higher perturbations, and Vx and Vy do not show any specific signature. Thus, when there are such storms, the plasma pulse come closer to the Earth, and you have also then formation of a plume. There's a kind of tail that you can see here that is formed in the afternoon sector, and that then corrotates with the Earth. Thus, the sun is in this direction here. Thus, the magnetic local time there is 12, this noon, and 0 in the night side is on the right of the figure here. Here you have dawn, 6 MLT, and this dusk here at the bottom. So here you can see a formation of a plume. This a small plume appears when the increase of Kp is not very high. This, it appears also for substorms. This you don't need very high events, but when you have high events, like here, for instance, in 2015, you have then a plume, this well visible, that corrotates with the Earth. Thus, that's when you have the storm, thus the plasmasphere is eroded, the plasma pulse comes closer to the Earth. After the storm, the index Kp decrease, and then you have the contrary effect. Thus, the plasma pulse goes further from the Earth, and then you have a zone between the vestigial plasma pulse 24 hours before in gray here, and the new plasma pulse in black here. You have a region here where you have refilling here also. And thus, it takes typically 2 or 3 days before the plasma pulse, the plasmasphere is again completely filled, and in between, then you have a boundary layer. This is not a sharp plasma pulse, but more thickness for the plasma pulse. Another mechanism that appears in the plasmasphere is the plasmaspheric wind. It happens only when you have very long quiet periods, and then the plasma pulse goes further from the Earth, slightly. This is in expansion, and you can see this the plasma pulse going further and further with time. And this is called the plasmaspheric wind that has been really observed by cluster satellites, for instance. So that's for the closed magnetic field lines. Thus, then the particles are trapped in the plasmasphere at higher latitudes. Thus, the magnetic field lines are open, and thus the particles can escape, and this is called the polar wind. Then there the number density is much lower than in the plasmasphere itself. And the plasmasphere, thus the particles from the plasmasphere come from the ionosphere with D, E, and F regions, as explained yesterday. Thus, what is really important is to note that the plasmasphere is the region in co-rotation with the Earth, and thus the drift of this particle, the drift velocity, is given by the electric force. Because in fact, the particles are trapped in the magnetic field of the Earth, and they have a specific motion. As if you assume that there are not many collisions because the number density is low, then you have this a superposed motion. Thus the particles have a gyration motion in the perpendicular plane of the magnetic field line, then a motion along the magnetic field line between mirror points, and then you have a drift, azimuthal drift. Thus, in the west for the protons and in the east for electrons, but only for the energetic particles. Thus, the particles that create, for instance, the ring current, and also the particles of the radiation belts. Thus, they create a current because the motion is different for protons and electrons. But for the particles of the plasmasphere, it's different because their energy is low. So their drift velocity is not due to the magnetic force that is proportional to the energy of the particles, but is due to the electric force. And this drift velocity is given by E cross B on B square, where E is the electric field, B the magnetic field. Thus, you have not creation of any current with the plasmasphere because all the particles, electrons and protons and ions, are in co-rotation drift to east with the same angular velocity as the Earth's rotation. And thus, in fact, this electric field plays a very important role, this for the co-rotation and for the plasmasphere itself. Thus, you have an interplay between the co-rotation electric field and the convection electric field that is due to the effects of the solar wind, and that will dominate at large distance. So at low distance, it's the co-rotation that dominates. And you can find, in fact, the co-rotation electric field. They're saying that the velocity, the drift velocity, this E cross B on B square, is equal to the velocity of co-rotation, just the frequency, the angular frequency of the Earth multiplied by the radial distance. Thus the angular velocity, it's 2 pi on 24 hours. The magnetic field you can replace, for instance, by the dipole magnetic field, just decreasing as the cube of the radial distance, and then you can find the value of the co-rotation electric field or the co-rotation potential, just at any distance and magnetic latitude. Thus here you can see the combination of the potential, the co-rotation electric field that dominates this at low distance. Thus at low distance, you have a circle here for the equipotential, the isoline of electric potential. Thus this corresponds to the region in co-rotation. At higher radial distance, it's convection due to the solar wind effects that dominate. This, there you have different models that can exist and that are KP dependent, just dependent again on the geomagnetic activity. This here I show you two different models. This, on the left, you have Wollenstern obtained from observation from OGO 3 and 5 satellites, for instance. And on the right, you have E5D obtained from ATS5 and ATX6 satellites. This, when KP is small, this, you have a large region in co-rotation, as you can see here. When KP increases, then the convection becomes stronger, and then you can see that the region where co-rotation is dominant is smaller. And this you have here. You have here. Thank you. This the region where the plasma pose is formed here in the post-midnight sector, because you can see that it's here that the gradient is the highest here for the electric potential. Just note that the plasma pose do not correspond to the last closed equipotential as it is sometimes assumed, and the plume is not especially the singularity point that you can see here, because you have this effect of co-rotation that has to be taken into account when you consider the plume. But of course, it's related to this electric field. There's another model that can be used also for the convection electric field. It's Weimer. It's based on the polar ionospheric observations, and it is controlled not by KP. KP is a 3-hour index, so it's not very high resolution. The solar wind effects can be more interesting if you want to make predictions, for instance. But because it's observations in the ionosphere and at high latitude, well, it's not ideal because, as we have shown, the plasma pose is more formed in the equatorial plane and at large distance. So, well, it's not especially the best one for the plasma pose position. So the particles come from the ionosphere. So the ionosphere is created mainly due to the ultraviolet radiation of the sun that ionize the particles of the atmosphere. Also, X-rays, cosmic rays, and solar particles are able to ionize the atmosphere. There are different layers, D, E, and at higher altitude, F1 and F2. And this one is the is the region where the ionization is the highest. As you can see here, in the model, the International Reference Ionosphere Model, created by Belitza, and improved every year. And that is available also on the PITHIA platform. You can see here the electron density as a function of the altitude, and you can see especially the different ionization layer. You have this D layer at low altitude, typically above 60 kilometers, and that this layer disappeared during the night. You have the layer E, F1 and F2, and you can see that it's typically around 300 kilometers that the maximum of ionization appears, and that it's made, of course, during the day that the density is the highest. And during the night, the layer do not disappear completely, even if the ultraviolet radiation is reduced, and thus the ionization is lower, but continue to exist. And you can see that at higher altitude, just for the plasmasphere, that continue, the density decrease exponentially with the altitude. And then it's mainly the solar activity that is important. The density is higher when the solar activity is maximum in comparison to maximum even during the night. And this, when the sun goes down, there's of course the maximum of ionization decrease, but the altitude increase slightly with local time. This layer was in fact formed after the first transatlantic radio emission made by Marconi in 1901. And it was not understood at that time how it was possible that transmission could be made at such a long distance between this America and England because of the sphericity of the Earth. And then this 1 year later, ELI-C and Kennelly separately proposed that it can be due to an ionized layer that can explain this long distance transmission. And it's only 23 years later that Appleton shows indeed its existence and that the altitude could be measured. And it was then called ionosphere in 1929, because otherwise it was called ELI-C, Kennelly, and Appleton layer. And note that Appleton and Marconi received Nobel Prize separately for this discovery for the ionosphere. Thus, the ionosphere is, of course, very important for the reflection of radio waves. This is the D layer, this only present during the day, reflects low frequency wave, E layer, the middle frequency wave, the sporadically, and the F layer, high frequency waves. For very high frequency waves, they are not reflected, and this can cross the ionosphere. And this explains this transmission at large distance, because you can have several reflections like this, and thus obtain transmission at large distances. This frequency are just indicative, because it changes a lot depending on the ionospheric conditions. What is important to note is that during the day there is a high absorption, especially in the D layer, because this is the region where the density is very high, and thus you have a high wave attenuation, because the oscillating electrons, these that oscillate with the same frequency as the radio frequency, they have a lot of collisions with the other constituents of the atmosphere, and thus you have a high absorption. Thus, the conditions of propagation are better during the night. And also when you have a flare, for instance, you have a higher absorption. Thus, the short waves have more difficulties to be transmitted, and the long waves this will be reflected at lower latitudes, lower altitude, sorry, when there is a flare. That's for the ionosphere. Thus, for the plasmasphere, it will also disturb, just for instance, the signal for the global navigation satellite system, because these satellites are located above 20,000 kilometers of altitude, and thus the GPS are not only affected by the ionosphere itself, but also by all the plasmasphere density. This here you can see the electron column density between 100 and 400 kilometers. Thus here during a quiet day. Thus then the maximum of ionization appears at the equator during the day. And when there is a storm, you can see that then you have also high fluxes and high densities appearing at high latitudes, and not only in the equatorial plane. Thus, the plasmasphere itself was discovered and at least confirmed much later after the after the ionosphere. It's only in 1963 that there was a proof of the existence of the plasmasphere and of the plasma pose by Carpenter in America and Greengross in Russia. And this region was postulated by Story a little bit before with the detection of Whistler waves. This, in fact, when you have lightning storms, thus you have a creation of such Whistler waves. This that corresponds to electromagnetic waves in very low frequency, between 2 and 20 kilohertz typically. And this Whistler thus propagates along the magnetic field from one hemisphere to the other, and they give a specific frequency time signal that allow to determine their existence, and also to determine the density of the electrons in the magnetic equatorial plane. And so we have, for instance, at our institute also, such kind of this VLF detector, Whistler detectors, that can be used also to study the plasmasphere. But of course, the main observations are made by the satellites. And well, what is also, why is it interesting to study the plasmasphere? Just because of its link with the ionosphere, but also the links with the other regions of the magnetosphere. Thus you have especially the radiation belts, Van Allen radiation belts. This very energetic electrons and protons also trapped in the magnetic field of the Earth, but coming not from the ionosphere, coming from the solar winds for the outer belt, and from cosmic ray, albedo, neutron decay, and solar proton neutron decay, just for the inner belt. There are these layers overlap, and of course there are interactions between these different populations. And there is also some interactions with the plasma sheets. The plasma sheet is this region where the magnetic field lines are much more elongated, and where you have several keV particles that are accelerated along the magnetic field lines and create aurora. Thus, in fact, what is very important is that the waves that will circulate inside and outside the plasmasphere will be completely different, because the density is so different that you have a lot of different waves, and these waves will interact and cause loss of particles in the radiation belts, for instance, also acceleration of the particles. And so for this, it's very important to know not only the number density inside and outside the plasmasphere, but also the position of the plasma pose. Here you can see the different waves. Thus, the main waves inside the plasmasphere are the His wave, plasmaspheric His, that can exist also in the plume, and this plume can be connected to the magnetopause. So this is an important cause of loss of particles, for instance. Then you have outside the plasmasphere, this, where the density is much lower, you have the Whistler mode chorus waves, especially in the night side here. And along the plasma pose, you have emic waves, this electromagnetic ion cyclotron waves, this, that are in resonance with the frequency of the plasma. And you have also magnetosonic equatorial noise that you can see here, and that will just interact with the different particles trapped in these regions. And this was especially studied recently with Van Allen probes observations. This in 2012, this two satellites called the Van Allen probes were launched by NASA with low inclination, and a very elliptic orbit. And it could cross just the plasmasphere and measure the density with emphasis and electric field wave instruments, and also the radiation belt with MAGAs, for instance, for the electrons. And so here you can see some observations. Just for instance, for the plasma pose location found by Van Allen probes that are also called RBSP, this radiation belt solar probe. Thus you have here the position of the plasma pose here between 3 and 6 Earth radii as a function of the minimum of DST index measured during the 24 previous hours. And you can see that even if there is a large dispersion, there is a clear trend that the plasma pose is closer to the Earth when DST is very low, like just when the minimum of DST is high positive. And here you have the same plots, but for the maximum of Kp during the 24 previous hours. And again, you can see the fit, the best linear fits that show a clear trend of a lower plasma pose position when Kp is high. This confirmed what was already known before with previous observations of plasma pose. But what is even more interesting is the comparison between the density of in the plasmasphere and the fluxes in the radiation belt. Here at the bottom, you have the density of the plasmasphere. This during 1 month, typically, or 2 months. This measured by emphasis on Van Allen probes. And the pink line corresponds to the plasma pose. And you can see here the plasma pose going closer to the Earth during a big storm, for instance, on this day. And here you have the fluxes for different energies. Just here for electrons above 1 MeV, here 1.6 MeV. And you can see with this, when you have this event, that you have a flux that is highly increases and penetrates at lower radial distances. This here, it's the radial distance McElwain parameter in Earth's radii. This it's come closer to the Earth and fill the slot region between the inner and outer belt. Just for 500 keV, you can see that this injection can even reach the inner belt and inject particles in this inner belt. And after the event, you have again the slot region that is reformed in a few days. And for lower energy, this here typically 100 keV, you can see again also these different injections that are even more frequent for each even smaller events. And thus you can see that are really the same kind of reaction, at least when you have a storm, this injection at lower altitudes. And thus typically we have found links between the boundaries of the radiation belts and the plasma pose. Typically when the activity is low, the plasmasphere is very extended, and the plasma pose corresponds to the outer edge of the outer belt. When the activity increases, the plasma pose comes closer to the Earth. And when it's very high, this, the plasma pose is very close, and you have also the outer belt that comes closer to the Earth. And for electrons corresponding to 1 MeV, thus the position of the plasma pose corresponds to the inner edge of the outer belt this time. So here you can see this plasma density here obtained was observed by the Van Allen probes in October 2013. And from this, we could deduce the position of the plasma pose here. And knowing just the number density inside and outside, we could calculate the diffusion coefficient, and here the pitch angle diffusion coefficients for two different energies. This here for the first event, beginning of October, and here end of October 2013. And from this, we can deduce the effects of these particles, of these waves on the radiation belts, and compare the results with the observation of the outer belt, and obtain especially the same variations during this month. Thus, each time you have an event, thus you have, as I explained before, thus when the geomagnetic activity is low, the plasma sphere is quite extended. You have here, for instance, a plasma pose around 5 Earth radii in the equatorial plane, and of course in the meridian plane as well. And this, if you project this, this, when the activity increases, you have this erosion here in the post-midnight sector, and then the rotation that gives the plasma pose closer in all magnetic local time. And it means that the projection of the plasma pose this, in the ionosphere, this is located at higher latitude when the activity is low than when the activity is higher. This, when the activity is higher, you can see that the plasma pose and projected in the ionosphere is located at lower latitude, and this corresponds this, in fact, to this mid ion trough in the ionosphere. Thus, it's not only the position of the plasma pose that is located at lower latitudes when there is a storm. Thus, when there is a storm, you have also the auroral oval just created by this injection of plasma sheet particles in the ionosphere. Thus, this auroral oval becomes brighter and also goes to lower latitudes when you have a storm due to a solar wind event, for instance. And thus we have compared, in fact, all these boundaries, this, the plasma pose location, but also the position of the auroral oval. And this we find that in general, the outer edge of the auroral oval correspond quite well to the plasma pose location, even if, of course, it's always located at higher latitudes. And well, for the radiation belts as well, this, the radiation belts here observed with a satellite at low Earth orbit, this at low altitude. Then it can see the South Atlantic anomaly, this due to the very low intensity of the magnetic field in this region. And the outer belt for the electrons, this corresponds to these bands here in the south and north hemisphere. If you project on the above the pole, then you can see that it forms also a kind of oval that becomes also brighter and decrease in latitude when you have these storms. All these regions are in fact connected, and all goes lower in latitude when there are storms. That was for electrons, or this aurora created by electrons, but you can have also proton aurora. This you can see spots like that. that were discovered by the satellite image and also observed by the satellite and DMSP. And in fact, because they are due to precipitation of proton of this energy by emic waves, they are always located again close to the plasma pose, because we have seen that these emic waves are close to the plasma pose. So a lot of new observations have been obtained with 2 satellites in the years 2010. This typically cluster and image. Then this a book was especially published about that, and especially the satellite image gave for the first time global views of the plasmasphere. Thus, in fact, this satellite was launched in 2000 with an apogee located quite far from the Earth. And thus, when it is located above the North Pole, it gives a global view of the plasmasphere, because it has an instrument called the extreme ultraviolet instrument that detects the light at 30.4 nanometers diffused by the helium ions of the plasmasphere. And thus you can see here the Earth, the auroral oval, but also this the plasmasphere in the equatorial plane with a sharp decrease in intensity corresponding to the plasma pose. So that was the first time we could have global view of the plasmasphere, and then it just in the equatorial plane, and thus it discovers that indeed the plasmasphere is quite extended and almost circular when the activity is low, and then the plasma pose is not very well defined. Now, many irregularities in the plasmasphere. And when the activity is high, you have this a sharper plasma pose closer to the Earth, and this plume appearing in the afternoon sector. You have also channel sometimes between the plumes. You have shoulders, notches. There's a lot of dynamic for the plasma pose. This cluster satellites were also launched in 2000. There are 4 satellites that are still active now, and that were launched with polar elliptic orbits, thus crossing also these different regions. And the cluster data are also available on the PITHIA platform that we will explain this afternoon. This cluster, the 4 different cluster satellites, give especially spectrogram like this with the instrument WHISPER, that gives the frequency as a function of time. And the clear blue line here corresponds to this frequency that is directly related to the number density of the electrons. And this is the number density of the electrons along the orbit of the satellite. When you have a sharp decrease like this, it corresponds to the plasma pose. This is the number density inside the plasmasphere. And sometimes there were some peaks like that were not really well understood. But by comparing with the satellite image, we could discover that it corresponds, in fact, to the extension of the plume. And for this, we needed this global view of the plasmasphere. This cluster were also used to make correlation between the plasma pose position and different indices. This here, there's many geomagnetic indices. Here I show you just the correlation for the DST index, because that's the best correlation that we obtain. And here also with solar indices. This here, the best correlation was obtained by the product of the velocity of the solar wind multiplied by the magnetic field intensity of the solar wind. As you can see, correlation quite high, to 0.7 typically, and especially in the post-midnight sector, this between 1 and 7 MLT sector, because this is really where the plasma pose is created. At other sectors, also you obtain good correlation, but you have to take into account a lag, because you have to wait that the plasma pose is transmitted to the other MLT sectors. So you can see that the lag increases to obtain the best correlation. And here, it's illustrated the BV, here the x-axis, as the position of the plasma pose. And again, you can see that you have this anti-correlation in this case. This when the BV is high, this you have a plasma pose closer to the Earth. And here you can see this the correlation study. This where you can see this time lag. This we calculate the correlation for all the time lags possible during the 30 previous hours, and just the MLT, the lag is increased when you consider increased MLT sectors. That was made not only with cluster but also with Themis, CREST, and many other spacecraft. Kaguya is also a very interesting Japanese satellite that is more recent, and like image, it can give global view of the plasmasphere, but not above the pole, but in the meridian plane in this case. You can see here an event where the plasma pose comes closer to the Earth, and this could confirm, in fact, the mechanism of interchange instability for the formation of the plasma pose. Thus, we can see the zero parallel force surface coming, eroding just the plasmasphere during an event. And well, to finish, I want also to mention a new discovery published this year in Nature for the plasmasphere. So there are many things still to discover. They discover lunar tides effects in the Earth's plasmasphere. Thus, in fact, the periodicities are distinct, diurnal and monthly, thus different from the semi-diurnal and semi-monthly variations observed for the ocean and for the ionosphere, for instance. So, to conclude and summarize, thus the plasmasphere is the extension of the ionosphere. The plasma pose position depends on the geomagnetic activity. It's closer to the Earth when the activity is high, during storms, but also substorms. It is formed mainly in the post-midnight sector. It's where the sharp gradients are observed. And so that's why you have a time lag in the other MLT sector before the plasma pose is transmitted in these regions. After the storms, you have refilling from the ionosphere. That takes typically 3 days. Plasmaspheric wind during plunge periods, and these observations come mainly from satellites, but also from ground-based stations of Whistler waves. It's very important to study this layer, not only for the radio waves and perturbations, for the GPS, for instance, but also because it influences the radiation belts and the other regions of the magnetosphere. So here you have some recent publications summarizing a little bit what I have mentioned here. Thank you very much.
Questions? Questions? Okay, it works.
Very clear or not a clear at all?
Thank you for the presentation. And you talk about the refilling mechanism of the plasmasphere, and I don't understand very well. So can you repeat it, please?
Yes. So
at the start.
So in fact, in fact, you have yes, the particles. Just to make it simple, you have the particles from the ionosphere circulate along the magnetic field lines. Okay, then when you have an increase of the activity, the plasma pose. The plasmasphere is eroded and the plasma pose comes closer to the Earth. Okay. that's what I explained. So you have here, for instance, the plasma bows coming closer to the Earth. Thus, when the activity decreases, you have the convection electric field that is less important. Just the co-rotation is again more important. And thus, you have the plasma bows going further from the Earth, okay? But it's not immediately that this region is again completely filled. Thus, there is a period of 3 days thus where you have a lower density in this region than this between the low plasma pose that was observed 24 hours before, just when the plasma pose was close to the Earth, and the region where the plasma pose is now further. And there you have not a sharp gradient like that, but you have more refilling. Just the density is more and more evolving to recover the number density as in the other regions. And then you find again a sharp plasma pose further from the Earth. Is it clear?
Exactly. Thank you.
Just because it takes time before the plasma, the particles from the ionosphere refill completely the flux tubes corresponding to this region.
Other question?
Okay.
Thank you.
Thank you, Viviane. May I ask you to close that microphone, please? So we move to the next talk. So I invite Sean. Am I right? Yes. Oh, sorry. Coffee break. That's right. I'm sorry. Okay, let's go coffee break. Let's convene in half an hour. I'm sorry.